Okay, you look like that. Okay, but we don't do that. We just flip everything, make everything go into positive. But can someone tell me what is the difference? Beside one is in the first quadrant, the other side is the third quadrant. Can anyone tell me what you can see? What you can talk about tensile and compression? Can anyone see any trend, please?
Rotational symmetry.
Right. Think about the magnitude.
Is it that a material is more likely to fail in tension than it is in compression?
Yep. So in general, okay, metallic alloys can withstand compression, stress, or compression load higher than tensile. Okay. So for metallic alloys, yeah, not for carbon fiber, but this is also true for what? This is also true for concrete, right? And if it's a ceramic material, it can only withstand compression. It cannot withstand any what? Tensile. So in general, in metallic alloys, okay, if we look at metallic alloys, metallic, okay, and I think you will learn this in 2P, right? The U, okay, the U in compression is about 15 to 30% higher when compared to tensile. Okay, so we can stand better compression loading than tensile loading. Okay.
Why is it that way? I mean, is it because of the property of the material?
It's because now we have to explain based on material science. You are hindering slip plane. Okay, you are reducing the material able to slip, especially in the shear configuration. Okay. Hello.
Okay, thank you. That helps.
Sir, is this because as you compress it, your area gets larger, and so you can distribute your force slightly better?
You can't say that. Okay, I do get what I mean, but this is comparing in terms of yield. Okay, so we are not looking into plasticity. So yield, the change in area is not very big, is it? Hello?
No, it's not. It's not big at all.
Yeah. So in terms of if it goes into plasticity, is also true that it's higher, but not necessarily 15 to 30%. You're right. You have bigger area, and the failure mode is different. Okay. Now I'm not going to teach failure mode in this course. Okay, that is a gadget course. Okay, so this is just information that you need to know for now. Okay. We have a course in the gadget program to literally prove to you mathematically why compression able to withstand higher stresses than tensile. Okay, now in the elastic region, right, in the elastic region, as you all know, the stress strain right, the stress and strain has a linear relationship, right? We know that we have the, and this relationship, and okay, which is known as Hooke's law. Okay, we call it Hooke's law. So Hooke's law. So we are now focusing on the elastic region. Okay, so if this is our strain, this is our stress, you see this is our Young's modulus, and we know to stress is equal to Young's modulus multiplied by strain. And this is basically Hooke's law. Okay, and we did derive how to calculate. So we know stress is equal to P over A. E is a material property, and epsilon is equal to change in length divided by original length. Okay, so the three most common material that is used, okay, that's regularly used. So if I have material, and I think it's important that you all try to remember these three materials. Okay, so the three materials we are looking at is steel, and then the next one will be brass, and then the last one will be copper. So these are the three most commonly used material. Okay, and if you look at the Young's modulus, okay, in terms of gigapascal, right, still we are sitting at 210. Okay, 200 to 210. Okay, brass is about 110, and copper at 70. Okay, then I'm going to put some use strength value. Okay, so I'm going to erase this. Okay, so we have some use strength. Okay, and these are in megapascal. So the use strength for steel, a certain type of steel, is about 650 megapascal. And then for brass is about 350. Copper being softer is about 250 megapascal. Okay. So if we were to sketch this out, okay, I'm thinking, should I get rid of this? Yeah, get rid of the stress strain curve. Yeah, why not? I can draw it again. Okay, so if we look at the stress strain relationship now, okay, so this is strain, this is stress. So we are looking at the elastic region. Okay, so I'm going to draw 3 lines. Okay, so this is one line. This is the other line. And the third line. I hope you can see the third line. Yeah, you can see. So can someone tell me this third line we're referring to which material? Anyone?
Copper.
Good. So this is our, I do apologize. I should not be writing this as copper. I do apologize. I look at my notes wrongly. This is aluminum. I do apologize. Can you change this to aluminum, please? Okay, so the first one that we've drawn is aluminum. And how about the next slope? Which one is it?
Brass.
Right. And the top one is steel. Okay. So not only you'll need to know what the numbers mean. Okay, you physically have to have the impression what the slope actually means. Okay. So the area. Okay, so the area under the stress strain curve okay, is known as energy. Okay. So if we were to calculate the area under the stress strain curve, you get the energy required to induce yielding of the material. Okay, so the elastic energy to deform the material is known as the modulus of resilience. Okay, so you do see this term modulus of resilience. So if mathematically, right, if you look at the math is real simple. Okay, so if we say that it's area under the stress strain curve, so what we have, so energy required, okay, to induce elastic deformation up to its U strength. Okay, so U elastic is equal to half times by base, okay, epsilon y, and times by stress U. Okay, so it's basically area. Okay, so basically what we did is just calculate the area down here for steel. Okay, this is just half base time height. Okay, so from here, let me declare what is epsilon y. Okay. So epsilon y, capital Y, is a strain. Is a strain at the U strength. Stress capital Y is known as U strength. Okay. Now we can also derive. Okay. We can also derive. Okay. We can also derive based on Hooke's law. All right. We can also derive this based on Hooke's law. Okay. So we know Hooke's law is okay. What I'll do, we come back to deriving based on Hooke's law when we come back from our break. So now it's 8:15. Go for a 15 minutes break, and we come back at 8. We'll be back at 8:30. Okay. So go and make yourself a coffee, drink some beer, or smoke something. Okay, and then come back at 8:30. I'll see you guys at 8:30.